Well, today I'd like to finish up what I didn't get covered last time because of the PowerPoint issues. I'd like to spend some time talking about capacitances and interconnects. I'll talk about back-end processing, and hopefully I'll move into a discussion of some of the devices we have to work with in the semiconductor process. Review from last time, we talked about patterning copper. Why was copper of interest to us for interconnects? Primarily one reason, yes?
Higher conductivity.
Higher conductivity than aluminum. A lot higher, a little higher. What? Somewhere around a factor of 2, right? And that's a big deal in this business. How long did it take to get copper patterning under control in the industry?
Quite a while.
Quite a while. A couple decades. Worked on it for a long time. A lot of smart people worked on it for a long time. What's the major reason we can't do the same thing with copper that we did with aluminum?
Electromigration.
What?
Electromigration.
No, electromigration is the benefit of copper. It's a little bit less effective than aluminum. But why couldn't we use the same processing steps we used for processing aluminum? Yes?
Well, you need to have the metal barrier, and you have to close that.
Okay, so one reason is the copper doesn't stay in place.
Yeah.
That doesn't have to do with why we can't pattern it, but okay, so there are 2 problems. One problem is that it migrates, but why can't we pattern it the same way we did aluminum? Yes?
It's difficult to etch.
It's difficult to etch. There's no volatile compounds of copper that can easily be etched away. So we went to a Damascene or a dual Damascene process. And what we did there was, conceptually, we just made holes, put the copper in the holes, and then ground the top off, and when we're done, we're left with the copper where we wanted it at. Okay. And then the 2 problems we pointed out then was the lack of the ability to etch it, and the fact that the copper doesn't stay in place. So you put barrier metals in to take care of the movement of the copper in the silicon. We talked about resistance interconnects. We defined a sheet resistance. A sheet resistance was related to the thickness of the material, the resistivity of the material, and we said that was sometimes more convenient to work with than the thickness of the material and the conductivity of the material. And we saw that if we had the sheet resistance, we could find the resistance by just multiplying an interconnect by the length and dividing by the width, or equivalently putting a number of squares on it and multiplying by the number of squares. It has units ohms per square, but per square is dimensionless. It's just a dimensionless quantity. I didn't go over this in detail last time, so let me mention it briefly. A lot of times when we build resistors, we use a serpentine layout. If you have a very large resistor, and if you want a very large resistor, it takes a lot of squares. It gets too large, too long to be conveniently put into a circuit. So a lot of times we'll fold it up. So this is called a serpentine pattern. And what we've done is we've added a few corners, but if you forget about the corners, we can stretch it all out. It's just one big long resistor. And the only disadvantage of this is we lose a little bit of efficiency in the corners because we only pick up about 0.55 squares in each corner instead of a full square. But if there's 100 squares across here, and every once in a while we have a 0.55, it really makes very little difference in regard to the area requirements. In order to find the area that is required to make a unit resistance, we can look at the square, pick out a square here, and then I have to allocate area to it that is associated with the spacing on the top and the bottom. And so I would probably allocate half of the spacing here and half of the spacing here. And if I did that, that would be a reasonable representative of how much area is required to make one square. Of course, since this distance and this distance are the same, they're equal to this distance from here to here is going to be the width of the poly plus the width of the spacing. So the area that's required to make one square then is going to be D1 plus D2. that'll be the height, times D1, because this is a square. And D1 and D2 come from the design rules if you're trying to make the minimum size resistor. Yes?
So why is the corner only considered as 0.55 of square?
That's a good question. And I didn't analytically show it, I just stated it. But if you have a conductor or a resistor that turns a corner, and you look at where the current's going to flow, it's going to flow pretty much uniformly out here throughout the whole region. And down here it's going to go pretty much uniformly, but it's going to crowd around the corner. So if you look at the square right here, you'll have almost no current in this outer part of the corner. But you'll have a real short path around this inner corner. So it tends to look like it would get bigger because of that outside part, but it looks like it would get smaller because of the inside part. This would suggest that it would have less resistance than normal. This would suggest it has more resistance than normal. So if you look at the combined effects, you can solve a Fields problem and show that it comes out to be about 0.55 squares. Okay, it's a good question. We didn't show it, we just stated it. Okay? Any other questions? Let's talk about capacitance and interconnects. We like capacitors sometimes, but we're making interconnects who don't like capacitors. They come along for the ride. They're considered parasitics. So let's look at a situation now where we have two regions that could be conducting. They could be resistive regions or metal regions, but there's a certain amount of conductivity in the two regions. I'm going to assume one is completely surrounding the other. So the yellow one completely surrounds the blue. The capacitance density is the capacitance per unit area looking down into the z direction, or in the screen here looking horizontally. And so if you look at the capacitance that you have between these two plates here, or these two conductors, it's equal to the capacitance per unit area times the area of the interlap, of the overlap. But since one is always bigger than the other one by my assumption here, the capacitance then is equal to capacitance density times the area of that blue region. Sometimes we have metal layers crossing each other, or metal crossing a poly, or whatever the case might be. So here I'm showing metal 1 and metal 2 sitting above substrate. And let's see what happens here. If I look from here down to the substrate, I see an insulator, because the insulator is used to be sure that the metal doesn't short out the substrate. If I look down from here, I see the substrate below. But if this is metal 2, it's up higher. So the distance from here down to the substrate is larger. And if I'm in this region in the middle here, I look down from that metal 2 and I see underneath it metal 1. And under metal 1, I see a substrate. So we form several capacitors here in this interconnect. From metal 1 to metal 2, which occurs in this region here, I have a capacitor, I'm going to call it C12. And from metal 1 to substrate, there's going to be an insulator between all this metal 1 and substrate. I'm going to call that C1s. And for metal 2 to substrate, in this region here and in this region here, I look down and all I see is a substrate. I'm going to call that C2s. So here's an equivalent circuit of the parasitic capacitance we see in this interconnect where there's a crossing of two conductors. Now this crossing could have a lot of area. You could have a bus that runs across a circuit You may not want to do this, but you could. Could be a 16-bit bus, and you're going to say, I'm going to put the first 8 bits on metal 2, and the next 8 bits on metal 3, and I'm going to run them like a superhighway, one stacked on top of the other. So there could be a lot of overlap between these two as well. So here might be a minimal amount of overlap if you let them cross each other in a perpendicular way, but they could run parallel to each other and on top of each other. And then the overlap area would be a lot larger. So let's calculate the capacitance. C12, capacitance from metal 1 to metal 2, is equal to capacitance density from metal 1 to metal 2, capacitance density from metal 1 to metal 2, times the area A5 here. That's the only place the two are on top of each other. How about the capacitance from metal 2 to substrate? Can we write that down? Well, there's only two places where you see substrate under metal 2. This region here and this region here. So it should be area 3 plus area 4 times the capacitance density from metal 2 to substrate. And the capacitance density from metal 1 to substrate, if you look at metal 1, it went down before metal 2, so all the way under metal 1, you see substrate below it. So the capacitance for metal 1 to substrate should be A1 plus A5 plus A2 times the capacitance density for metal 1 to substrate. Is that clear? So we look at, yes?
I'm just a little bit hazy on why you don't count that A5 twice.
It figures, let me put two things up and then we'll go back and answer your question. So what I just described, I've listed here. So the question was, when you look at the capacitance from metal 1 to substrate, why don't you count A5 twice? Okay, so if you imagine you're on metal 1 and you look down below you towards the silicon wafer, what do you see underneath? So if you're on metal 1 and look below metal 1, what do you see?
Substrate.
Just substrate. And what is the area that you have for metal 1 where you see substrate below it?
A5. Or A1, A5.
A1 plus A5 plus A2 is just one smooth layer, right? So that capacitance there should be A1 plus A2 plus A5 times the capacitance density of metal 1 to substrate. It is counted twice, but it's counted a second time because it also affects the capacitance between metal 1 and metal 2. So when metal 1 and metal 2 intersect, all you see is area A5. So that's why we had A5 times capacitance density of metal 1 to metal 2. So it appears twice in this expression, in these expressions. Once from metal 1 to substrate, and once from metal 1 to metal 2. Does that answer your question?
I guess so, yeah.
I'm not convinced.
Sorry, the main thing was just like that metal 2 A5. Why you don't count that capacitance between that and the substrate?
We do. So here's one capacitor from here to substrate, from metal, and that's A1 times C capacitance density from 1 to substrate. And then here's one capacitor, and it's A2 times capacitance density from metal 1 to substrate. Now I haven't taken care of this part in here yet. So underneath that, I also see substrate, but that area is just A5.
You mean the substrate in between metal 2 and metal 1?
There's no substrate in between. The substrate is the wafer we start with. So if you look at how this is fabricated, we'll have substrate here. Someplace out here there might be some transistors. And if we have this interconnect, there'll be a big insulator here. This is an insulator. And on top of the insulator, if you look at this cross section, we'll see metal 1. This is metal 1. On top of metal 1, I'm gonna see some metal too, but I'm only gonna see a little bit of it across here in this region here. So here was metal 1, and here is metal 2. So if you're on metal 1 and look down, you see substrate. If you look metal 2 down, there's no substrate below it that you see. You're stopped by a conductor in here.
So there's nothing in between metal 2 and metal 1.
There's an insulator in here. This is an insulator.
Something with a very, very low capacitance.
No, it might be very high. This distance is pretty large. So this is all insulator in here. So there's insulator on top of metal 1, an insulator below metal 1. The insulator is necessary to separate metal 1 and metal 2.
Okay.
So there's only one thing, it's called a substrate. That's the silicon wafer we started with. On top of that, we put an insulating layer. On top of that, we put metal 1 and patterned it. On top of that, we put another insulator. On top of that, we put metal 2 and patterned it. Okay?
That makes sense.
Good. Any other questions? Yes.
What is C12 measuring capacitance of between again?
Capacitance between metal 1 and metal 2. Right here.
Oh, okay.
Here's our circuit model, and here's the component values.
Oh,
Okay? Of course, we'll talk about in a bit. These capacitance densities are part of the model parameters for the processor. So the only way you get those is talk to people that made the process to find out what those parameters are. They're part of what you call the process delivery kit, or PDK, that describes the process. Part of the interface between the process engineers and the design engineers. Here's another example where we have two regions that overlap, but one is not always bigger than the other one. So here I might have metal 1 and metal 2. Metal 1 is this region, metal 2 is this region, and they only intersect in this region here. So again, we can determine the capacitances. Determine the capacity between metal 1 and metal 2. Well, the only place metal 1 and metal 2 intersect is in this region right here. So the area of the intersection is 20 microns by 20 microns. So the area of the intersection is 400 square microns. And we multiply that by the capacitance density from metal 1 to metal 2 to find the capacitance from metal 1 to metal 2 on this structure. Is that clear? Yes?
Can you define capacitance density in maybe a different way?
Capacitance density is capacitance per unit area. So the way you oftentimes make a capacitor, the way you almost always make a capacitor, is you take two conducting plates, and you separate them by the insulator. So here's one plate of a capacitor, here's another plate of a capacitor. Now, if you look at the capacitance between those two plates, it's epsilon A over D, right? So the capacitance between two plates is equal to epsilon times A divided by D. That was what you probably had in your physics course already, right? Now, D is fixed for a process. So if I want to know what the capacitance is between two plates, I can either remember epsilon and D, or I could lump them together, because they won't change for the process times the area. And by definition, this is capacitance density. Okay, so the capacitance density then is epsilon over the thickness, or it's the capacitance per unit area. Does that answer your question?
Yep.
Okay, other questions? If the capacitance density of metal 1 to metal 2 is 0.07 femtofarads per square micron, then we multiply that by the 400, and we find out we have a capacitance here of 28 femtofarads. So you can look at Moses' website to get process parameters. I'm giving some of the parameters right here. This is usually attached to the homework assignment. I must have missed it this last time. These are, got to be a little bit careful. These are measured parameters. The actual parameters that the manufacturer tries to target are considered to be confidential. They're proprietary. So we can look at measured parameters. They're real close to what the manufacturer tries to achieve. So we'll pretend these are what you're designing to. Are you with me? So these are measured parameters.
Why are they confidential?
Oh, I don't know. You go to industry and ask anything about the process. Oh, can't talk about it. But I can tell you one reason. If you know very much about your competitor's process, you know what the performance characteristics are, you know what their costs are. And that gives you a real advantage in the marketplace if you know what your competitor has to spend for making the parts. Because everybody doesn't have the same process. Some people have better processes than others. Make sense? So they guard that information pretty closely. Furthermore, they don't want other people who put a process together to know necessarily how to target the characteristics. We're working on a design right now that's due in about 2 weeks. And there's an ion implant that actually comes in at an angle relative to the surface of the wafer. And the angle depends upon the orientation of the substrate. We made the mistake of asking the supplier of the process yesterday. We said, what angle do you implant at? Proprietary. So, you know, a lot of things like that they're real sensitive about. So this lists some of the model parameters of a transistor. We'll get back to that later. The threshold voltage and so forth are listed here. If we go down on this list, here's the parameters I'm interested in. If you look at capacitances, this is the capacitance from every layer to every layer. You can create a lot of capacitors in a process with a few levels of metal. This happens to be a 2-metal process. So you read this table. If you want to look at the capacitance from metal 1 to metal 2, so here's metal 1 to metal 2. The capacitance is 31 attofarads per square micron. The capacitance from poly, let's see where, poly to metal 1 is 56 attofarads per square micron. The capacitance from metal 1 to substrate, here's a substrate to metal 1, 27. Substrate to metal 2, 12. Substrate to metal 3, 7. Why do you think the capacitance densities go down when you go from metal 1 to metal 2 to metal 3?
Because the distance is greater.
The distance is greater, so we have less capacitance density. Yes?
This is unrelated to this, but we had the same list in the homework,
Yes.
and where on that list does it mention the dimensions for like the minimum width and minimum spacing for like the
Design rules are not given here.
Okay.
But if we say a 0.5 micron process or a 20 nanometer process, then you know what there's a minimum feature size for that process. In the laboratory, we've been working on a 180 nanometer process, and your minimum widths, I think, are 200 nanometers, I believe. Okay. That you have to be given what the minimum feature size is in the process and the process parameters. Conspicuously absent are numbers over here. Well, I could fill it out. It's symmetric. It's a matrix here. And if I wanted to put stuff in here, the capacity from A to B is the same as the capacity from B to A. Okay, so you only have to list it once. There's one thing here that's very interesting. One of the capacitance densities is higher than anything else. And that's this right here. And that's substrate to poly. And when it's substrate to poly over thin oxide, you form your transistors. So this is the capacitance per unit area of the gate. Remember we said the gate area, the gate thickness, the oxide underneath the gate was real thin? If the oxide is real thin, it has a high capacitance density. So we see a real high capacitance density from poly to substrate. That's COX. We're going to call that COX later. Oh, here's the resistance, sheet resistances. Notice you can use anything to form a resistor about as well. You can use N plus diffusion, P plus diffusion, poly, metal 1, metal 2. Metal 1 doesn't make a great resistor. Well, it makes a resistor. It's actually a pretty good resistor, but it doesn't make a very big resistor unless you have an incredibly long length on metal 1. Yes?
I mean, the units for those capacitance is absurdly small. How do they get those values out of the machine that's able to calculate capacitance for that low ROS?
Yeah.
Okay.
The question is, can you measure them?
Yeah.
Well, two things. First of all, you know the epsilon. You can use a scanning electron microscope and measure the thickness of the layer. You can calculate what it would be.
Okay.
If you want to measure them, if you have an area that's really, really small, there are clever circuits that can actually infer what these capacitors are, even though they're so small. Remember, we asked the question, is that 1.5 femtofarads that you have for that gate capacitance of a transistor negligible? Well, our conclusion was no. Why was it not negligible? It affected the rise and fall times. So you can work backwards and say, gosh, if I could measure the rise and fall times, could I infer what that capacitance was? And the answer is yes. Okay, so there's a lot of clever techniques people have for measuring even very small capacitors, not necessarily directly. But the other way you do it is you'll make it big. If you make the area big, then you have something you can measure, and then you can scale it down. Yes?
The model we built using the capacitor is not entirely accurate.
The what?
The model we built using the capacitor is not entirely accurate.
You mean capacitance density times the area?
No, the model we had for the transistor using the capacitor.
Oh yeah, it's not real accurate yet. We're going to improve on it later.
But we can still use that to use the rise and fall times.
Yeah, that's right. We're going to come back later and do a better job of calculating what COX is, and do a better job of calculating capacitance. It's not far off for a minimum-sized device and a 0.5 micron process. Oh, notice also there's some that have kind of weird dimensions. Something per micron. So what we find is that if you make a capacitor, if you have a diffuse region, we're going to start talking about this on Monday. We're going to see that there's a capacitance formed between the N and the P-type material on the bottom. We're going to also find there's a capacitance formed on what's called the sidewall. So the total capacitance along the sidewall then will be the capacitance per unit length times the perimeter. The capacitance on the bottom is the capacitance per unit area times the area. So these have to do with fringe capacitors that are on sidewalls of devices. Here's a bunch more parameters for BSIM models and so forth, so don't worry about those right now. Example, determine the resistance and capacitance of a poly interconnect that's 0.6 microns wide and 80 microns long, and compare with the same interconnect if metal 1 was used. So here we have a poly interconnect. Resistance of the poly is the number of squares times the sheet resistance. Number of squares is 800 divided by 0.6. And the capacitance is the area times the capacitance density. And the area is 0.6 times 800 microns squared. So we need to get the sheet resistance. And the capacitance from drain to poly, not the resistance. So the sheet resistance for poly 1 is 23.5 ohms per square, right here. And the capacitance from poly 1 to substrate, if it's not on thin oxide, when it's used interconnect, is 84 attofarads per core micron. Okay. So let's go back and see what happens. And the capacitance density, we have 84 attofarads per square micron, so we can plug back into those two equations. Number of squares is 1300, so the area is 480 square microns. The poly resistance is then 1333 times the sheet resistance, which was 23.5, so it's a 31.3K resistor. And the capacitance is the area times the capacitance density, comes out to be 40.3 femtofarads. 40 femtofarads is a pretty good sized capacitor on a piece of silicon. If we have metal 1, we just repeat the process. We just have to look at different places. Sheet resistant metal 1 is 0.09 ohms per square, and the capacitance from metal 1 to substrate is 27 attofarads per square micron. So we can plug that back in and find we have 120 ohms and 13 femtofarads. A lot of difference in the resistance and a lot of difference in the capacitance. We talked about planarization before. It just has to do with replanarizing the surface after we've done processing steps. Let's talk a little bit about the back-end process flow. After you have your wafer come out, you do several things to it. By the way, a new fab and state-of-the-art process is somewhere around $10 billion right now, with a B. Pretty big investment. The back-end processing is much, much less expensive. When you do wafer probe, where we go in and try to take measurements before we break the wafer apart to get some idea whether the circuit's good or not. Then we do wafer dicing, which means we break the wafer up into die. Then we do die attach. That means we attach the die to a package or to a carrier. And then we do wire attach, put bonds in, finish the packaging up, hopefully test it and ship it. So this is the back end processing steps. Here's how dicing takes place. You have a bunch of blades that rotate, and you index the wafer first in the X direction. That makes traces along it. Then you rotate the wafer 90 degrees and go the other direction. You may have to change the spacing of the blades if it's not a square die. Okay. That cuts them apart. Die attach. You've got to put the die now into a package. You don't want it to float around. We have 3 ways to do it. A eutectic bond, a preform, or conductive epoxy. With a eutectic bond, if you have gold on the back of the wafer, you can show that if you put 2 pieces of gold together and wiggle them a little bit, they'll stick. That's called a eutectic bond. Sometimes it's ultrasonic vibration that takes place, creates a little heat, and they stick together. A preform is you take a thin film of solder. So like a piece of aluminum foil, maybe much thinner, cut out a little square of it, lay it in the package, put your die on top. If the die has something that solder will stick to on the bottom, then you heat it up and the solder melts and you've attached your die to the package. Conductive epoxy is pretty explanatory. You just put glue in the bottom of the package, stick the die on and let it dry. Unfortunately, all three of these steps are typically done at accelerated temperature. Yes?
You mentioned something about having dies that are not square.
Yeah. Sometimes they're rectangular. They might be 2x1 or something. So then, when you saw them, you have to change the spacing of the saw blade so that you still go down between the die.
Do you get much sawdust from this process?
Oh, it's nasty. You get polysilicon, mostly. You have single crystal silicon, and you get all the silicon dust out. The fact that this die attach is done at a hot temperature is kind of bad. Because if you look at that die after you saw it apart, that die is this nice rectangular type structure. What happens when you heat it up? You got to melt solder, you heat it up. So I'm going to look at this face here. This face, when you heat it up, I'm going to exaggerate. It's going to look like a pillow. Does that make sense? You heat it up, and as it expands, the device no longer stays rectangular. It's kind of puffed up in the middle too. On this surface here, it's kind of puffed up too. When it cools down, it goes back to normal size, right? No, wrong. You've got solder underneath it. So you heat it up, let the solder melt, and then cool it down. It's still pretty warm when that solder melts. It's still not back to its relaxed condition. Solder melts and it sticks. So what does the die do? It would like to return to its previous shape, but the solder won't let it. So what does that do to the circuit? Or to the die?
Warps it.
It what?
Warps it.
It warps it. It's now warped. It puts stress on it. And that stress will change the characteristics a little bit. Does nature like stress?
No.
No, nature doesn't like stress. We try to relax things out. And as things relax out over time, it will gradually get a little bit flatter. That means the characteristics of the circuit, if they're affected by stress, might drift with time. Make sense? As that die relaxes out. Bonding. We do two things. Wire bonding is probably still the most popular, where we connect. So here's the die sitting in a package. This is the package. Here's the die sitting in a cavity. And we have bonding pads here. We have to connect a wire between the bonding pad and a corresponding landing pad in the package. Connect wires there. How many wires do we have to connect?
Depends on the chip, right?
Depends on the chip. Some chips probably have as few as 2 wires. Some may have as many as 400 or more. That's a lot of wires we have to connect if you have 400 wires. The wire is typically 25 microns of diameter. It's usually gold or aluminum. Oftentimes it's gold. Here's kind of how it looks if you do wire bonding. You put a wire ball down on the die and you smash it down. So it's warm and you put pressure to it, and gold is malleable. It kind of bends and so that ball gets deformed and it looks something like this. It's hot and it sticks. Then you slide it over here, go down and push it on the package and push hard, maybe wiggle a little bit, it sticks again, and then break it off there and you've got your bond. If there's 400 pads, you do that 400 times on one die. So here's kind of a picture, shows how it goes on. You start with a ball on the bottom of this capillary. It's called a capillary. Here's the wire coming in here. Then you go down and mash the ball down. And the mashed ball down looks like this. Then you pull it up. When you pull it up, then wire comes out of the capillary like this. You see the mashed ball down here. Then you move the capillary over to the side. Wire continues to pull down through the capillary. Then you push it down on the package and make it wiggle it, and it sticks, and you pull it up and break it off. So here it broke, and we don't have a ball there yet. So then we typically do a thermal flame off. We run a flame across it. It's oftentimes a hydrogen flame, and that causes that gold to melt on the end and form a little ball. And then you're ready to repeat the process. Here's an expanded view of what that capillary may look like. So here's the 25 micron hole, plus just a little bit so the wire slides through it. And this is what mashes the ball down. So that's really magnified a lot, that capillary. These are actual photographs of a ball bond. And you can see where the ball was mashed down here, and there's the wire that we had on top. Here's the termination bonds on the other side. You see the wires coming down here, and you see the imprint of the capillary here when it was mashed down. Here it shows a whole bunch of bonds that were put together. There's a ball bond here going over the package. Here we have two wires going to one pin on the package. Why would we want to put multiple wires on maybe? Homework assignment 1, did we talk about that? You gotta get a lot of current in, right? And maybe one wire won't carry enough current, so you might have to put more than one wire in. You can put bumps on it. So here are our solder bumps. Here you flip the chip over and just mash it onto the package. And the goal is to have all the bumps the same height, so when you mash it down, you make interconnects on all the bumps to the package. Eliminates the wire bonding process. You can see that there's a lot of bumps there. We're making a lot of interconnects between the die and the package. A lot of different packages available. I'm not going to go through them. There's literally dozens and dozens of different packages that are available. There's a lot of work going on today in stacking die on top of each other. Again, for a time reason, I'm not going to go through that, but that's one way we're increasing the density right now of our integrated circuits. We'll put 2 or 3 or 4 or 5 die in one package maybe. And this kind of shows how they go together. Let's not do that. Most ICs are tested twice. Once at the wafer probe before it's taken apart, and once after the packaging is done. The reason we do it twice is because if you package a bad part and then you test it and throw it away, you have to throw away not only the die that was that lousy in the first place, but you throw away a good package. So if you can detect the die that are going to fail before you package them, you don't have to incur the cost of a package when you throw that die away. So we typically don't do extensive tests at the wafer probe. We try to screen out the dead on arrival die. We'll do more extensive testing after it's packaged. Let's talk a little bit about the semiconductor. So that's pretty much a discussion of the back-end processing. Let's talk about the device we have available to work with. So first of all, let's kind of review some of the different processes. There are some processes called NMOS processes. The key device in those processes are the N-channel transistor. We have some PMOS processes. The device available there, primary device, is a P-channel transistor. CMOS process, we have both N-channel and P-channel transistors available. The process we're working with in this course is the CMOS process. These are less expensive. They were introduced earlier than the CMOS processes. They're still used for some real cost-sensitive parts where power dissipation and size are not a big concern. If you want a real inexpensive part, power dissipation is not a major concern, then these are the processes to go with. In the CMOS processes, the basic device is the MOSFET. There are some niche devices, the BJ, the MESFET. And in all of these processes, there's some other devices around that really come along for the ride. You can use them if you want. We're going to see that a diode is available, oftentimes a BJT, resistors, capacitors, and a Schottky diode. The characteristics of these devices are what they are. We try to make good MOS transistors. We end up with these other devices. It's kind of like use them if you want, but we don't optimize the process for these other devices. In the bipolar area, remember bipolar came before MOS in production. We have TTL processes. That was the dominant form of logic probably up until about 1990. We have emitter coupled logic. Emitter coupled logic is faster than TTL, and the supercomputers probably up until maybe close to 2000 were made out of ECL. I2L, a lot of linear ICs. Many of the op amps and a lot of the other ICs you'll buy today are still made in bipolar processes. In a bipolar process, we typically have a good diode. We typically have a good BJT. And then we have some resistors and capacitors that are probably not as good. Some other processes that are worth mentioning, there are thick and thin film processes. In these processes, the basic device is a resistor. And in the thick film processes, they're screened. You screen the resistor much like you screen the t-shirt or the sweatshirt that you have on. That went through a screening process. Instead of putting ink to make it look white, that you'll put a resistive material in that has a certain resistance per unit area. Thin film processes are very similar to the process we use to make transistors. Oftentimes the feature sizes are much bigger, so the equipment is not as expensive. There's BiMOS or BiCMOS processes where we have good bipolar and good MOS devices available at the same time. Those processes are much more expensive, so they're more used for niche applications because of their cost. Silicon germanium. So instead of having used a silicon process, we have silicon germanium bipolar transistors. Silicon germanium bipolar transistors are really fast. So if you need a lot of speed, SiGe might be the route to go, although in many cases, companies will start a design in SiGe because they think they need the speed, and by the time they get nearly done with the design, somebody else has figured out how to do it in CMOS, and the market for SiGe is not there. SiGe MOS. Some of the silicon germanium processes also have good MOS transistors available. You're starting to get real expensive processes now. These are exotic processes with really nice devices. Silicon on insulator and silicon on sapphire. Instead of having a crystalline silicon substrate, you have an insulating substrate, and you build up your single crystal material. Twin well and twin tub or triple well processes, they're types of CMOS, offer some performance benefits over the bulk CMOS that we work with in this course. Primary considerators in this course is going to be a standard CMOS process. We're going to have N-channel and P-channel transistors available, capacitors, resistors, diodes, maybe a BJT, not too great, maybe a JFET, and we'll have some niche devices that we'll look at as well. We will spend some time in this course talking about SCRs and triacs. It's an entirely different type of process that's used to build those types of devices. So, let's talk about the devices now. The resistors. I won't spend much time talking about resistors for two reasons. I only have 2 minutes left today. And second, we already talked about resistors. We talked about resistors as a parasitic device on interconnects, but you can also use them as a component. So they're generally thin film devices. The thickness is very small compared to the lateral dimensions. Almost any layer can be used to form a resistor, poly or N plus or metal or whatever. they're often temperature and voltage dependent. So if you measure the resistance as a function of temperature, it's typically not going to be constant. Sometimes there's local heating. When you put current through the resistor, it warms up. Sometimes they're voltage dependent, which means that it'll introduce nonlinearities in your circuit. Some of the resistors we have are trimmable. You can go in with a laser and trim some of the resistors that we have available. All of these resistors are subject to process variations. So what you get today and what you get tomorrow is going to be a little bit different. If you go across the wafer, the sheet resistance might not be the same in the middle of the wafer as on the end, or not necessarily even the same on the middle of a die as it is on the end of a die. There's also local random variations. Resistors are formed much like snowfalls. And snow, if you have an inch of snow, it's a little bit higher, a little bit lower, because you've got individual snowflakes forming that snow. Well, the same thing is true of resistors. You try to make them the same, but they don't come out quite the same even if they're real close together. So here's the resistor model we had before. We talked about the sheet resistance before. I don't need to go through this. We've already gone through this. Let me close with this slide. Here's the resistivity of some of the different materials we use for processing silicon. You can use any one you want. How much variation do you have in resistivity for these different materials? From silicon dioxide at one end to copper at the other end. How much difference in resistivity or sheet resistance? What?
Quite a bit.
Quite a bit. Enthusiasm! An order of magnitude? No, it's more than 14. It's 20 orders of magnitude difference in the conductivity of materials. That is dramatic. That's all for today. Thanks.